The grounding electrode conductor, or GEC, should be bonded to the metallic panel board or transformer at the point where it enters the enclosure. The purpose of this bonding is to ensure a low impedance path for fault current to flow to the grounding electrode system. However, if the ground bus inside the metallic panel board or transformer is bonded to the enclosure, it is acceptable to bond the GEC to the ground bus. This is because the ground bus provides an alternative path for fault current to flow to the grounding electrode system. The reference for this is NEC section 250.32 bone. As for the jumper size, the bonding jumper used to connect the GEC to the metallic panel board or transformer should be sized in accordance with the requirements of NEC section 250.66. This means that the jumper must be insulated unless it is run in rigid metal conduit or intermediate metal conduit, IMC, size for the current carrying capacity required by NEC table 250.95, and at least the same size as the GEC, but not larger than the service entrance conductors. However, if the GEC is sized for a current rating of 100 amps or less, a jumper of smaller size may be used for the bonding connection, provided that firstly, the jumper is at least 2 American wire gauge AUG, size is smaller than the GEC, and secondly, the jumper is rated for the current carrying capacity required by NEC table 250.95. The reference for this is NEC section 250.66C3. It is important to ensure that the bonding connection is properly made using approved materials and methods to ensure a reliable low impedance path for fault current. Let's delve into the details of grounding electrode conductor, or GEC, bonding within metallic conduit systems, focusing on National Electrical Code, or NEC, requirements. The primary aim of bonding the GEC to metallic enclosures is to establish a reliable, low impedance path for fault currents. This path is crucial for the effective operation of overcurrent protection devices, such as circuit breakers and fuses, which interrupt the flow of electricity during a fault condition, thereby preventing electrical shock hazards and minimizing equipment damage. NEC section 250.32 bone offers guidelines for bonding the GEC in separately derived systems. It stipulates that the GEC must be connected to the metal frame or enclosure of the separately derived system. This connection ensures that any fault current flowing through the system will have a direct and low impedance path back to the grounding electrode system. The grounding electrode system typically consists of electrodes such as ground rods, metal underground water pipes, or concrete encased electrodes, all of which provide a connection to the earth, offering a safe path for dissipating fault currents. Now consider the scenario where the ground bus within a metallic panel board or transformer is already bonded to the enclosure. In such cases, NEC section 250.32 bone permits the GEC to be bonded to this ground bus. The rationale behind this allowance is that the ground bus itself provides an alternative, yet effective, path for fault current to reach the grounding electrode system. However, it is paramount that the connection between the ground bus and the enclosure is robust and properly maintained to guarantee a consistently low impedance path. Moving on to the sizing of bonding jumpers, NEC section 250.66 outlines the criteria for determining the appropriate size of bonding jumpers used to connect the GEC to metallic enclosures. The general rule is that the bonding jumper must be sized based on the size of the service entrance conductors. For instance, if the service entrance conductors are rated for 200 amps, the bonding jumper must be sized accordingly, as specified in NEC table 250.66. The NEC also mandates that the bonding jumper be insulated unless it is installed within rigid metal conduit, or RMC, or intermediate metal conduit, or IMC. The insulation serves to protect the jumper from corrosion and physical damage, ensuring the long-term reliability of the grounding system. There is an exception to the general rule regarding jumper size. According to NEC section 250.66C3, if the GEC is sized for current rating of 100 amps or less, a smaller bonding jumper may be used, provided certain conditions are met. Firstly, the jumper must be at least 2 American wire gauge or AUG, size is smaller than the GEC. Secondly, the jumper must have a current carrying capacity sufficient to handle the ground fault current, as determined by NEC table 250.95. For example, If the GEC is an 8 AWG copper conductor, a 10 AWG copper conductor may be permitted for the bonding jumper, provided it meets the current carrying capacity requirements of NEC Table 250.95. It is crucial to recognize that proper installation techniques are essential for ensuring the effectiveness of bonding connections. The bonding connection must be made using approved materials and methods, such as listed bonding connectors and fittings. These connectors are designed to provide secure and reliable electrical connection, minimizing the risk of loose connections or corrosion, which can compromise the integrity of the grounding system. Moreover, it is vital to thoroughly clean the surfaces of the metallic enclosures before making bonding connections. Removing any paint, rust, or other contaminants ensures a good electrical contact between the bonding connector and the enclosure. The bonding connection should be tightened to the manufacturer's specified torque to ensure a secure and long-lasting connection. Periodic inspections of bonding connections are also recommended to identify and address any potential issues such as loose connections or corrosion. By adhering to these best practices, you can ensure that the grounding electrode conductor, or GEC, bonding within metallic conduit systems is performed in accordance with NEC requirements, providing a safe and reliable electrical system. Let's now focus on practical examples and additional considerations related to bonding grounding electrode conductors GECs in metallic conduits. Imagine a scenario where a new electrical service is being installed in a commercial building. The service consists of 250 kcmil copper conductors and a 4 AWG copper GEC. The GEC is routed through a metallic conduit to a ground rod located outside the building. According to NEC section 250.66, the bonding jumper connecting the GEC to the metallic service equipment must be sized no smaller than the GEC itself, which in this case is 4 AWG copper. Therefore, a 4 AWG copper bonding jumper would be required. Now let's consider a different scenario involving a smaller electrical service in a residential dwelling. The service consists of 100 amp service entrance conductors and an 8 AWG copper GEC. The GEC is routed through a metallic conduit to a ground rod. In this case, NEC section 250.66C3 permits the use of a smaller bonding jumper, provided it meets certain conditions. The bonding jumper must be at least 2 American wire gauge, AUG, sizes smaller than the GEC, which would be a 10 AWG copper conductor. Additionally, the 10 AWG copper conductor must have a current carrying capacity sufficient to handle the ground fault current, as determined by NEC Table 250.95. Suppose a panel board is fed from a transformer. The transformer's secondary windings are grounded, establishing a separately derived system. The GEC for this system runs in metallic conduit to a grounding electrode. The NEC requires the GEC to be bonded to the transformer enclosure at the point where the GEC exits the conduit system. A bonding jumper is used for this purpose. The size of this jumper is determined by NEC Table 250.66, based on the size of the transformer's secondary conductors. It's worth noting that the NEC provides flexibility in choosing the type of grounding electrode system. Common grounding electrodes include ground rods, metal underground water pipes, and concrete encased electrodes, often referred to as UFO grounds. The choice of grounding electrode depends on site conditions and local requirements. When multiple grounding electrodes are present, they must be bonded together to form a comprehensive grounding electrode system. This bonding ensures that all electrodes are at the same potential, minimizing the risk of voltage differences that could create hazardous conditions. The NEC also addresses the bonding of metallic water pipes used as grounding electrodes. It requires that the metal water pipe be supplemented by an additional grounding electrode, such as a ground rod or a concrete encased electrode. This requirement is intended to provide redundancy in the grounding system in case the metal water pipe becomes compromised or disconnected. Another important consideration is the proper installation of grounding and bonding conductors. These conductors must be installed in a neat and workmanlike manner, and they must be protected from physical damage. The NEC prohibits the use of staples or other fasteners that could damage the insulation of grounding and bonding conductors. The NEC also provides guidance on the identification of grounding and bonding conductors. Grounding conductors are typically identified by the green color or by a green color with one or more yellow stripes. Bonding conductors may be bare or insulated, but they must be permanently and visibly identified as bonding conductors. Now, let's discuss some common misconceptions about grounding and bonding. One common misconception is that grounding conductors are intended to carry current during normal operation. In reality, grounding conductors only carry current during a ground fault condition. Their primary purpose is to provide a low impedance path for fault current to return to the source, allowing the overcurrent protection device to trip and clear the fault. Another misconception is that bonding is only necessary in metal conduit systems. In fact, bonding is required in all electrical systems, regardless of the type of wiring method used. Bonding helps to equalize the potential between different metal parts of the electrical system, reducing the risk of electric shock. It's important to stay up to date with the latest edition of the NEC, as the code is periodically revised to reflect changes in technology and industry best practices. Local jurisdictions may also have additional requirements that must be followed. Consulting with a qualified electrical inspector or engineer can help ensure compliance with all applicable codes and regulations. Remember that proper grounding and bonding are essential for electrical safety. By following the requirements of the NEC and adhering to best practices, you can create a safe and reliable electrical system that protects people and property from the hazards of electricity. Consider the scenario where a building has multiple electrical services. Each service must have its own grounding electrode system, but the grounding electrode systems must be bonded together to form a common grounding electrode system. This bonding ensures that all services are at the same potential, minimizing the risk of voltage differences between them. In high-rise buildings, the NEC requires the installation of a vertical grounding electrode conductor that runs from the main service grounding electrode to the remote building steel. This conductor provides a low impedance path for fault current to travel back to the source, even in the event of a ground fault on an upper floor of the building. The NEC also addresses the grounding and bonding of sensitive electronic equipment, such as computers and servers. It recommends the use of isolated ground receptacles and dedicated grounding conductors to minimize electrical noise and interference. Isolated ground receptacles have a separate grounding conductor that is isolated from the normal equipment grounding conductor. This helps to prevent noise from other equipment from contaminating the grounding system of the sensitive electronic equipment. Now let's explore the role of surge protective devices, SPDs, in grounding and bonding systems. SPD are designed to protect electrical equipment from voltage surges caused by lightning strikes or other transient events. They work by diverting the surge current to ground, preventing it from damaging sensitive electronic equipment. For SPD to function effectively, it must be properly grounded and bonded. The grounding conductor for the SPD must be as short and straight as possible to minimize impedance. The SPD must also be bonded to the grounding electrode system to provide a low impedance path for the surge current to dissipate. The NEC also provides guidance on the grounding and bonding of swimming pools and spas. It requires that all metal parts of the pool or spa, including the metal reinforcing steel in the concrete shell, be bonded together to form an equipotential bonding grid. This grid helps to equalize the potential between different metal parts of the pool or spa, reducing the risk of electric shock to swimmers. The NEC also requires the installation of ground fault circuit interrupters, or GFCIs, for receptacles located near swimming pools and spas. GFCIs are designed to detect small ground faults and quickly to energize the circuit, preventing electric shock. Regular testing of GFCIs is recommended to ensure that they are functioning properly. And it's a good practice to conduct regular inspections of grounding and bonding systems to identify and address any potential issues. Look for signs of corrosion, loose connections, or damaged conductors. Any problems should be corrected promptly to ensure the continued effectiveness of the grounding and bonding system.